We previously discussed the formation of the hydrogen molecule H2 from two hydrogen atoms. And what we said is that the hydrogen molecule results from the overlap of the 1s orbitals of two hydrogen atoms. This allows them to share a pair of electrons. All right, now this is commonly referred to as the valence bond theory of bonding. Now, when two hydrogen atoms overlap their 1s orbitals to form H2, a sigma bond is formed. Okay, now a sigma bond results when orbitals overlap along the interatomic axis of the atoms involved in the bond, or there is head-on overlap of the orbitals. Okay, now an important corollary to this is the principle of maximum overlap. This was a principle that was developed by Linus Pauling. And what this says is that the strength of a bond between two atoms is directly proportional to the amount of orbital overlap. The better the overlap, the stronger the bond. The worse the overlap, the weaker the bond. Valence bond theory explains much of the bonding and structure of organic compounds. However, there are cases where the valence bond approach falls short, and so an alternative theory of bonding has been developed. And this is the molecular orbital approach. Right, when atomic orbitals in atoms overlap, they form bonds. Now, the electrons in these bonds must also reside in orbitals, and these are molecular orbitals. So atomic orbitals overlap to form molecular orbitals. Now, one of the important tenets of molecular orbital theory is that molecular orbitals are linear combinations of atomic orbitals. Okay, so this is commonly referred to as LCAO, linear combination of atomic orbitals. And what this means is that the number of molecular orbitals is equal to the number of starting atomic orbitals. Okay, so let's now look at the hydrogen atom, sort of our favorite simplified example. So here we have the hydrogen atom. This is the 1s orbital, and there is an electron in that orbital. Okay, so we have a second hydrogen atom, and this is in a 1s orbital, and there is an electron in that orbital. Now, if you recall, these orbitals have phases. Okay, so for the 1s orbital, the phase can either be red or blue, or plus or minus. Okay, so we'll use the algebraic terminology of plus and minus to describe the phase of the orbital. These phases are arbitrary. Okay, so the 1s orbital can either be of the plus phase or the minus phase. And so when we bring these orbitals together to form the H2 molecule and the molecular orbital, we must consider both phases. Okay, so one way that we can bring the orbitals together is in phase. Okay, so this is the plus phase for both orbitals now can overlap to form a molecular orbital. Now, the two orbitals being of the plus phase overlapping is the same as if they were both the minus phase. All right, now the other way these two orbitals can be brought together is out of phase. That is, the plus orbital of one hydrogen atom and the minus orbital of the other hydrogen atom. All right, now please look at this representation of that orbital, and note that we now, in the molecular orbital, we have a change of phase, right? So we go from a plus phase to a minus phase. And whenever you have a change in phase, you have a node. Okay, so in this orbital of H2, this molecular orbital, there is a node. Okay, and a node is where there is no electron density. Okay, so if there is no electron density between these two nuclei, it's really not much of a bond. Right, so when you bring orbitals together out of phase, it is of higher energy than when you bring orbitals together in phase. Okay, so this energy is the bond energy of H2. Okay, so this is now bringing the two atomic orbitals in phase, and so this is referred to as a bonding orbital. When they're brought together out of phase, this is higher in energy by the same amount, but in the opposite direction. And this is referred to as an antibonding orbital. And it is often denoted by putting an asterisk or a star next to the orbital designation. Okay, so we have the sigma bonding orbital and the sigma antibonding orbital. All right, now we have two electrons, we have two orbitals, so the two electrons can now fill the bonding orbital, and the antibonding orbital is vacant. All right, now a few other notes. The sigma bonding orbital is referred to as the highest occupied molecular orbital, or the HOMO. Okay, so that is the highest energy molecular orbital that is filled. And the sigma star, or the sigma antibonding orbital, is referred to as the lowest unoccupied molecular orbital, or the LUMO. Okay, now some of you may be wondering, if the antibonding orbitals are empty, what good are they, and why do they have to be there? Well, first, the math requires that they're there, and second, the antibonding orbitals are very important in explaining molecular properties and reactivity, and we will be developing this as we go through the course. Now, some of you may be familiar with an instrument called a Spec 20 from your AP Chemistry course. Now, if you recall, with the Spec 20, you put a solution that it was in a sample holder into the instrument, and that caused a signal to be read off of the instrument. Okay, and the magnitude of that signal was dependent on the concentration of the solution. So what the Spec 20 is actually doing is it is shining light through that sample, and that sample is absorbing some of that light, and that is causing one of the electrons in, say, a bonding orbital to be promoted or to jump to the antibonding orbital. And that is from the highest occupied molecular orbital to the lowest unoccupied molecular orbital. Okay, and that wavelength is related to the energy difference between those two orbitals. Okay, so that is one example of where the antibonding orbital is important in explaining a property of a molecule.